Advent of Code 2024 never ceases to provide amazing programming challenges. So in the last 5 videos we did the first 5 challenges, and today we're going to round off day 3. The first challenge for this day is easy to put into words, but not trivial to implement. We were given a long string like this, containing several instances of this kind of pattern. We have mul open parenthesis, then some number, comma, some more numbers, and a close parenthesis. And we were supposed to find all occurrences of that within the string. And if you watched that video, you know that the solution that I wrote then looks like this. We looked for the mul open parenthesis by hand. But I said in the video that this would have been the perfect use case for regular expressions in a normal programming language, but Funciton doesn't have regular expressions. But if you've been following my channel chronologically, then you know that I did implement something like regular expressions in Funciton. Which means that the Funciton library now has functionality in it, which lets you do something similar to what a regular expression engine does. And of course I did use this Advent of Code problem in that video to create this as an example program that can solve this particular challenge by finding that particular pattern. So here's a quick summary of how that program worked. We start with this, which is the integer representation of the string mul open parenthesis. And we turn that string into a lazy sequence of its characters, and then we wrote this function which allows us to turn that string into a regular expression which will match exactly that string, mul open parenthesis. And I'm using that same thing here to create a regular expression that will match the comma. But of course in between those two we needed to match a number consisting of digits. So we wrote this function which will return a regular expression that will just simply match any number of digits and return the parsed integer for it. And this function here allows us to glue these together so that we end up getting a single regular expression that will match each of these things in sequence. So we end up with mul open parenthesis, then a number, then the comma, and then another copy of the number because we're feeding it into here as well. And then we have this processing operation which will take the two integers and multiply them, because that's what the Advent of Code problem is asking us to do. And finally down here we have the close parenthesis. So what comes out of here is a regular expression that matches that whole thing, which is equivalent to a regular expression that looks like this. I wrote this in a comment to document what the program does. And then we feed that regular expression as well as the string coming in from standard input, also converted to a lazy sequence, into this function, which executes the regular expression and finds us all of the matches. And it will return a lazy sequence of all of the matches found, or more precisely, the result value associated with each match, which is the result of this multiplication. Then we sum them all up and convert that to a string and output that, and that is how we solved that Advent of Code problem. Now at the end of that video I said this. Now let me try and make a guess as to what the sequel to this one might be. Now the example input has a mul with square brackets in it, and also one here where the opening thing is a parenthesis and the closing is a square bracket. I have a suspicion that we're supposed to support square brackets as well, but not mixes. And now that I've thought about this, I've decided that I'm actually going to implement that first before I look at the next challenge. And the reason for that is because at the end of the regular expression video, I said this. And of course there are many other new operators that I haven't gotten to yet, most notably the alteration operator, the one that is written with a vertical bar or a pipe in normal regular expressions. So what I want to do first is I want to turn this regular expression into one that will match either the round parentheses or the same thing but with square brackets. And of course the first thing I need to do to make that work is to implement the alternation operator, the vertical bar. But of course we can't actually use the vertical bar character because that's already the absolute value function. So I'm going to use the Latin letter dental click. I don't know how I could make the difference any clearer. Anymore?
Yes, got it, sir.
So what do we need in order to implement the alternation operator? Now remember that a regular expression is a lambda expression that will take some input string and will return to you a lazy sequence of matches, but only the matches that start at the beginning of that string. The alternation operator of course takes two regular expressions as input, and it's supposed to return a new regular expression that can match either one of them. What do we want our final regular expression to return? That's right, we just want it to return all of those matches. So all we have to do is just concatenate them. So all the alternation operator needs to do is return a regular expression, which is of course a lambda expression that takes input, so let's start by putting that down. As a reminder, I'm using str to indicate the input to the lambda expression, but it's not actually a string, it's a lazy sequence. I'm calling it a string because in the majority of cases you will want to match against a lazy sequence of characters, Unicode characters. But the system is flexible enough that you can match against a lazy sequence of anything. And of course on the ESALang's wiki page we can see that we already have a function to concatenate two sequences. So let's just use that. And the two sequences that we want to concatenate are the results of calling each of the two regular expressions. So let's put a lambda invocation on both sides of the concatenate function. We don't care about the second output of those lambdas. And we need to make sure that we concatenate them in the right order. We need the first one to be the first regular expression that was passed into the operator because we want to prioritize it. And the input that we pass into these regular expressions is str. Now let's write the declaration box where R1 and R2 come out of. But now the parameters are in the wrong order because I put R2 here, but this is the first parameter. So I'm going to put a U-turn on the bottom of the function in order to swap them. Now let's join up str. And finally, we don't care about the second output, so let's just output 0 there. And now if I haven't made a mistake, I think that's the alternation operator. I told you it was going to be simple. Now back to our program where we wanted to match either mul parentheses or mul square brackets. So in order to implement this, we would need to take a copy of the entire regular expression that we already have, which I admit is not going to fit on the screen, but we don't need a duplicate of this comment, so let's get rid of that. And since this is going to be the second part of the alteration, let's change this one to be square brackets. Now this number here encodes mul open parentheses, so we need to change this to a different number. And as I'm sure you remember from previous videos, we have a helper program that can do that for us. So this is the string representation of mul open square bracket. So let's replace this big number with that. This number is the comma, so that will stay the same. This one here is the close parenthesis. So we need to find out what that is. And of course it is the Unicode code value for that character, which happens to be 93. So let's change that to a 93. And now let me scroll to the right and remove this part of the program because we don't need to duplicate that. Instead, we should move that a little down so that we can have some space for the alternation operator. And now let's see if this variant of the program works. As before, I'm going to use the example input provided by the Advent of Code puzzle page. So let's run the new variant of the program on that input string. And we get 182. Now the puzzle page says that the expected answer is 161, but we should now also be counting this, which is 21, so we expect 21 more, which would indeed be 182. So it's working! And it's worth noting that it correctly ignored this part where you have an open parenthesis but a closed square bracket. Those don't match, so it doesn't include that in the sum. So now it's time to see what the second challenge of this day actually is. If my guess was right, this is the end of the video. Part 2. There are two new instructions that you'll need to handle. The do instruction enables future mul instructions and the don't instruction disables them. Oh, that is interesting. Only the most recent do or don't applies. At the beginning of the program, mul instructions are enabled. Okay. So it's completely different from what I thought, but equally interesting. For example, so we include this because we include everything at the start, and then we have a don't, which means that this one is not included even though it would match the regular expression. And then eventually we reach the do here, and then the last mul needs to be counted again, which means that this time the result is 48. Okay, now this is interesting. This is also a perfect use case for alternation, but we now need to decide what to do with each mul instruction depending on what we've seen before. So here is how I'm going to do it. I'm going to create a regular expression that is going to match either mul as before, or do, or don't. And in our previous version, the mul was associated with the result of the multiplication. I'm going to change this so that it will be associated with the result of the multiplication, shift left 2. What this will do is it will make sure that the bottom two bits of that number are always 0, and we can always reconstruct the result of the multiplication by just shifting it right again. And then I'm going to have the do instruction return 1, and the don't instruction return 2. If we look at those in binary, you'll see that those fill exactly those 2 bits. So for the example input given in the puzzle, we're going to end up with a mul instruction giving us a result. In this case, 8 shift left 2, which is 32. Then a don't instruction, which gives us 2. Then 2 more mul instructions with their associated result. Then a do instruction, which gives us 1. And then the final mul instruction, which gives 40, which after the shift left gives you 160. And now that I have a sequence of these numbers, I'm going to use the aggregate function, also known as fold. And we can have the aggregate function start with a starting value, and I'm going to make that starting value 1 for a reason that will become obvious in a second. And I'm going to use this aggregate function to progressively process each of these matches, and at each point I will use 1 bit, the least significant bit, to determine whether we're inside a do or a don't, and the remaining bits to keep track of the total, because we need to add up all of the multiplications. So we look at the first entry, we notice that its bottom 2 bits are 0, which means that this is a mul instruction, so we need to look at the bottom bit of our running total, but our running total is shifted by only 1 bit, so we need to shift the result from the mul instruction right by 1 in order to fix that. Then the next entry we encounter is a don't instruction. In this case, we'll notice that the bottom 2 bits give us 2. At this point, all we want to do is just set that least significant bit to 0 to keep track of the fact that we are now inside of a don't. Then we'll encounter another mul instruction where the bottom 2 bits are 0, but this time, looking at the bottommost bit of our running total, we'll notice that we're inside a don't and we will not add it. Eventually we get to the do, where again we look at the bottom 2 bits and it gives us 1. So in this case, we want to set that least significant bit back to 1, and then our final mul instruction is once again going to be added onto the running total. And then what comes out at the end is the running total, but shifted left by 1 bit, so we can just shift that out, and then that will give us the result of the sum. So let's see, how do we need to modify our program to accommodate all of that? Well, the first thing we need to do is to modify this processing function, which processes the result of a mul instruction, by shifting the result left by 2. Now the result of the multiplication comes out here, so I need to move things around. Next, we need to tack on the alternation operator and create a regular expression that will match do, open parenthesis, close parenthesis. But now remember that we needed to associate that regular expression with the value 1. Now this is what the function looks like that takes a constant regular expression. And if you remember the regular expression video, we've associated every match with the number 0, because we didn't know what else to associate it with. But I think I'm going to introduce a variant of this function where you can just specify the result value directly as a second parameter. That function should come in handy now. So coming back to the program, we now want to pass in not just the string do, open parenthesis, close parenthesis, but also the value 1. And then after that, we need basically the same thing again, but this time with the string don't, which is considerably longer, and the number 2. So far so good for the regular expression part. Now let's match the regular expression against the input. And now what comes out of here is the sequence of those processed values that I talked about, either 1 or 2, or the result of a multiplication shift left 2. And we no longer want to calculate the sum of that, we want to run the aggregate function on this. Now the order of the arguments for the aggregate function is the sequence comes first, and then you want the starting value, which we've agreed should be 1, and the third input should be a lambda expression that accepts 2 inputs, the running total so far, and the next value from the input sequence. And let's feed 0 into the output that the aggregate function doesn't care about. Now at the end of the program, when the aggregate function is done, the last thing we need to do is shift right the number by 1, and then convert that to a string. And now the rest of the logic is entirely inside of this lambda expression here, but I can't be bothered to deal with this limited space, so I'm going to abstract that away into a function. So the interesting part is, what should that function do? Well, let's quickly write it down in pseudocode. Now remember that the first lambda expression receives the previous running total, and the second one receives the next value in the sequence, but the order in which I've put them into this function is kind of back to front. The first argument is the next value, so we need to keep that in mind. So let's think about what we want this function to do. We get the next value first and then the previous value. Now the first thing we need to determine is the least significant 2 bits of the next value. And how do we do that? Well, we need to bitwise AND with a binary number that has the lowest 2 bits set, so binary 1, 1, which in decimal happens to be 3. Now, if that gives us 0, then we're processing the result of one of those multiplications. So next shift right 2 is going to be the result of a multiplication. But remember, we want to add that onto the running total only if we are in do mode rather than don't mode. So how do we determine if we're in do mode? Well, the current running total, which I've called prev, we need to check the lowest bit, so we need to bitwise AND that with 1. And if that gives us 0, well then the result needs to remain unchanged, so we're just going to return prev. But in all other cases, we need to do the addition, so we want to return prev plus something, and we want to add the result of the multiplication. But remember that we need to shift that left by 1 in order to preserve the do or don't bit at the bottom, which means that if we now put in the value here that we have for mul, if we just substitute that in here, you'll see that we're doing shift right 2 and then shift left 1, which is the same as shift right 1. Let me put that in parentheses to make it clearer. Now, if the least significant 2 bits were not 0, then it's either a do or a don't. So we need to update the least significant bit in our prev value and keep the rest intact because the rest contains our running total. So at this point, we know that next is either 1 or 2. Now, if we look at these in binary, we'll see that 1 is actually 0, 1, and 2 is actually 1, 0. And this is the do case, and this is the don't case. And you'll notice that the do case has a 1 in the least significant bit, and the don't case has a 0. So why don't we just extract that least significant bit, and then change the least significant bit in prev to that? So we need to return prev, but we need to first remove the least significant bit. So we're going to bitwise AND it with the negation of 1. And then we're going to bitwise OR it in order to place the last bit. And the last bit is next and 1. This should be reasonably doable in Funciton because all these bitwise operators are literally just nands. Alright, let's start implementing. What is the top level operation in this function? Well, it's this if. So let's start with a question mark box. Now remember, the question mark function already checks for the equal 0. So the true case is actually the part that needs to happen when it's not 0. And on the top level of this, we have the bitwise OR. Let me just add some parentheses here to make this clearer. And we write a bitwise OR by writing a bitwise NAND, where both of the inputs are negated. Now next is going to be the first parameter, so I expect that to come out on the left of the declaration box. So I'm actually going to put this next AND 1 over here on the left hand side. Now how do we do a bitwise AND? That's right, it's a bitwise NAND, but negated afterwards. So we can actually cancel that with this negation and just get rid of it. Meanwhile, on the other side, we also have a bitwise AND, so we can do exactly the same thing. But before I do that, let's think about what the negation of 1 is. Well, it's a number consisting of all 1 bits except for the lowest bit being 0, which means that it is actually 1 less than negative 1, so it's negative 2. Now, what about the other branch on the question mark? Well, that would be this part. And I forgot to put the word if here, let me just put that in. And now we will see that we need another question mark. I wrote this wrong here. This is supposed to say least significant 2 bits, which is of course next, ANDed with 3. So let me implement that next. So I want to bitwise NAND with 3, and then negate the result of that. And at this point I'm finding out that we're going to have a next here, and this question mark is going to have multiple prevs. So I think it would actually be more convenient if these were the other way around. So let me quickly switch that. Now let me make more space by removing some of the code here that we no longer need. And now we just need to implement that if over here. So the condition is prev and 1 equals 0. So let's put that as the condition of that question mark. Now if the result of that is equal to 0, then we'll be on the false branch. So this should say prev. And then the true branch should be this. So we need an addition here. And finally, we need to implement the next shift right 1. So let's make a little bit of space here and put the shift right function here. Except that I've decided to actually write this as shift left negative 1, because as we all know, shift left is more fundamental to Funciton. And now all of the prevs are on the left side, so let's join them all up. And then we can write the declaration box right here, and then we can just join up the nexts. So now if I haven't made a mistake, this should be the correct function. So let's remove this pseudocode and let's scroll back up to look at the rest of the program, We can now zoom out to see the whole thing. And I'm just going to put that function over here in this empty space so I can zoom in again so you can see this a little better. And now comes the big moment. Let's run this program with the input string provided by the Advent of Code puzzle, and we get 48. And according to the puzzle page, that is indeed the right answer. But this could be a fluke. The only way to be sure is to run this program on the full puzzle input. So now I want to run that program with time measurement on the entire puzzle input, which of course I've obtained and put into a file. And I fully expect this to take a while because that file is reasonably large. And it looks like it took 7.8 seconds and it gave me an output, which I'm going to paste into the answer box, and it turns out that is the right answer. And we are 1 gold star closer to finding the chief historian. That was day 3, and these programming challenges have already caused me to add an entire new feature to the Funciton library. Who knows what else is gonna come up? So, day 4. Will you be there?